Physics is me, you, and us. Why do we study it? How can we understand quantum mechanics, relativity, the Big Bang Theory, and our universe? All of this and more are discussed by Dr. Niseem Magdy at the YouTube channel Nesentron.
So actually that takes us to, I would say, one of the main points for our interview today, which is the string theory. And according to my reading, I used to read, since it's out of my field, about the string theory. And then I will say it was maybe, to me, a little surprising to know that the idea originally was developed to describe the strong interaction before the QCD come, or the quantum chromodynamics, which the theory described the strong interactions. So that's precisely what I'm working on. I'm working on the quantum plasma, which is strong interacting system. And I think it was Viniziano when he tried to use the this idea of string as a replacement for the current blown.
Well, Viniziano did not think about strings. He had a mathematical formula.
Oh.
He had a mathematical formula for scattering amplitude. You know what a scattering amplitude is.
Yes.
And he had a mathematical formula which was a function of the momentum of the incoming particles and the outgoing particles. And it was a famous formula. It was called the Viniziano amplitude. But it was just a mathematical formula. It had two gamma functions in the numerator and one gamma function in the denominator.
Okay.
And it had a lot of interesting mathematical properties. Very interesting. Neither Viniziano nor anybody else knew what the underlying physics of it was. To them, it was just a mathematical formula. It was Nambu and myself who realized that it was describing the scattering of strings. Up until that point, the word string didn't appear in physics. If it did, it probably had to do with somebody's mathematical study of violin strings or something.
No, yeah, I was reading about it, and I think that was maybe the one part that was not getting straight. Yeah, what I observed in the book, he was putting the formula, as you just said, the Viniziano amplitude, and they was say, okay, the guy was trying to say how the quarks will interact together, what's sticking them together, and he was putting that as sort of substitute for it, and then of course later we know that something else is doing this, with the quantum chromodynamics. But I think as you just mentioned, you guys picked that at least the from there, but at that time it was not a string yet. It was not called even a string yet.
Yeah, now quantum chromodynamics came along. It was a quantum field theory, but as it turned out, quantum chromodynamics described strings. It was a mathematical field theory that was describing string-like excitations. So the string idea for hadrons, for strongly interacting particles, came together with the quantum chromodynamics ideas, and they turned out to be the same. We now know that protons, neutrons, mesons really are string-like excitations. They can be vibrated. They can be...
It's a field excitation, as I understand.
Well, it's a field excitation, but more than that, it's an object. It's an actual object which behaves like a string. An electron does not behave like a string, or a photon does not. You can't excite an electron. You can't cause the internal structure of the electron to vibrate. Not in the laboratory, you can't. At one time, it was thought that you could excite the internal structure of an electron and it would become a muon. That a muon was a vibrating internal vibration of the electron. That, of course, turned out not to be true.
Okay.
But
cool idea still.
But mesons and protons and neutrons do have vibrational excitations. You can take, or even rotational excitations. You can take a proton, and if you hit it just the right way, you can start it spinning with a higher angular momentum. You can cause its energy to increase, its mass to increase. the excitations have different names. The excitation of a proton is called a delta 3/2 or something. I don't even remember anymore. But those are protons which are vibrating.
Yeah.
Right? Or spinning.
Yeah, I can imagine that. We had the whole program called the proton spin. This try to study the internal structure from the
Right. The proton has a spin, but it also has an internal structure. It's made out of things.
Yes.
Those things, when they're excited, behave like, for example, a meson. A meson behaves like two quarks connected with a string.
Yeah, I mean, just for our audience, a meson is a particle that contains two quarks, and then another baryon will be a particle.
Well, it contains two quarks, or a quark and an anti-quark, but there is also energy stored in the string between them.
Yep.
So you can take those two quarks. Let's see, I'm trying to take those two quarks. Here they are, and you can hit one of them, and it will fly. They'll fly apart, but then they'll come back together again.
Oh, okay.
Vibrate.
That's like,
and that's the string. So string theory really was the right theory of hadrons.
Yeah. Based on what I learned, which I do all the day, mostly, I agree that what we think, what we learn.